Hello. Today we will learn one new tool in probability, how to compute certain types of uh, process where you could determine the probability of what happens at each step along the way. Then after that, we're going to look at a game that has a really surprising result. So I think you'll enjoy it. Let's jump to the tool that we will be using. Okay, so what we'll be learning is called probability trees. But let's look at some problems. So let's say you have an urn. That's my drawing of an urn on the right that has a certain different colored balls in it. So let's say 3 red balls, 2 green balls, and 3 blue balls. And then when you reach in and grab one, you can't feel by hand which ball is which color. And then we'll ask some questions about um, the event that will happen as we pull the balls out. So let's say we draw 2 balls out randomly without replacement. So that means that when I draw one ball out, let's say it's red, we're gonna pull out the second ball without putting the ball that you just pulled out back. So that's called drawing without replacement. And let's compute the probability that they're both red, right? So one way to represent like all the possibilities and probabilities with this is to like break it up into a 2-step process. We're drawing 2 balls. So the color of the first ball and then the color of the second ball depending on what you pulled out after the first one. So because there are 3 red balls out of 8 total in the urn, the probability that we draw the red after the first draw is 3/8. And similarly, probability of getting green is 2 out of 8 and blue is 3 out of 8, just based on what's already inside. If we're computing the probability that they're both red, we don't have to go further with the green and the blue situation. It only matters if we drew out red first, and then for the second ball, there are now only 7 balls left, and out of that, 2 is red. So 2/7 would be the probability that the second ball is also red. And then 2 out of 7 for green and 3 out of 7 for blue. And if I want to compute the probability that both of the balls were red, what you do is you look at these branches and multiply all the numbers along the way. So we want to consider the situation where we get red first, then red again. You multiply 3/8 to 2/7, and we get the probability that that occurs. So you just kind of, this is called the tree because it kind of branches away like a tree. And then you just multiply, you look at the path that you're interested in, and then multiply each of the probability in each branch along the way. So that's how a probability tree works. Let's look at a different problem. Let's say, what is the probability that they're different color balls? So we draw 2. What's the probability that they're different? We could start out the same way. So we can draw 3 branches for the 3 colors we get on the first one. We could break this each up into 3 more and end up with 9 different leaves. But since all we care about is it's the same color or a different color on the second step, we could split into 2 pieces. So after drawing a red, there's 2 red color that's left. So 2/7 for drawing the second red, or otherwise it's a different color. So 5/7 of the time, we'll get 2 different color balls where the first one was red. If you draw green, then the other is 6/7 because after the green is taken out, all of the balls except for one of them is green. And then 3/8 and 5/7 with the blue color, blue and something else. So what we do is there's 3 different leaves we're interested in. We're interested in 3 cases where you draw one color and you draw another color. So these are each of these possibilities, right? Red first and something else is 3/8 times 5/7. Green and then something else is 2/8 times 6/7, and the 3/8 times 5/7 for blue, and then something else on the second draw. We can multiply this out. It's actually easier if you don't reduce the fraction as you multiply them, because then you can get a common denominator and then you add it up. 42 out of 56. You could reduce that to 3/4 if you could. There's a common factor of 14, I think. So the probability that you'll get 2 different balls, 2 different colored balls, is 3/4, 75%. I hope that made sense. So you could, sometimes it might be difficult to ask, like, hey, what's the probability that this happens after 2 draws? What you could do is break it up into steps, and you could write down the probability after certain events happening after the first draw. So that's what probability tree is about. Okay, I hope you found that useful. Let's jump right into the worksheet. Okay. All right. So what we're going to talk about in this worksheet is about non-transitive things. So transitive means property that kind of propagates as you chain different things. So for example, if you are talking about numbers, if number A is greater than number B, and if number B is greater than number C, then the first thing, the A is greater than C. So that's the greater than relationship has what's called a transitive property, because if you stack them, you can kind of chain it and you get that relationship from the first thing to the next thing. It turns out that this doesn't have to be true with dice or something that has probabilistic component. Example of a non-transitive dice is as follows. So let's say you have 3 different dice, and they might be dice, but they have different numbers written on the sides. Let's say they have 3 sides, or if you don't want to think about a 3-sided dice, that's a really weird shape. They do exist, but maybe it's a 6-sided dice, and 2 of the faces have these numbers. So you could think about it that way as well. So if you have a dice with 3 numbers, 2, 4, and 9, and they're equally likely, 1/3 probability each, and another dice 1, 6, 8, and the third dice 3, 5, 7. First of all, there's no common numbers between these, so there's no ties. And then if you compute the probabilities of which die beats another die, it turns out that it's non-transitive. So A die will beat B, and B will beat C. And when I say beat, I mean more than 50% of the time they beat it. And die C beats A more than 50% of the time as well. So it kind of goes in this rock, paper, scissors type of relationship. It's non-transitive. And how would you compute something like that? Well, we could use something like probability trees and break up the die rolls into 3 parts. A turns out to be 2, 4, or 9. And then after that, let's say A is rolling against a B. So there's 3 different possibilities. So B is equal to 1, B is equal to 6, B is equal to 8. So 1, 6, 8, 1, 6, 8. Okay, let's keep track of which leaves on the end A wins. So each of these branch is 1/3. I'm not gonna draw 1/3 in all of these branches because it's kind of getting cramped. But okay, if A rolls a 2, the only way A could win is if B was 1, right? So then this is the case where A wins. If A is a 4, again, the only way A could win is if B is 1. So that's a possibility. If A is 9, that's the highest number there is on all three of these dice. So it doesn't matter what B happens to be. In all three cases, A wins. So each of these branches 1/3. So 1/3 times 1/3 is 1/9. 1/3 times 1/3 is 1/9. And each of these leaves are also each of them 1/9, but there's 3 of them. So I guess I could just write this as 3/9. And then if I add all of these leaves together, we get 5/9 as the probability that A will beat the die B. And 5/9 is more than 50%. So A beats B 5/9 of the time. I hope that made sense. So what I want you to do is pause this video and see if you can work out the probability that B beats C and the probability that C beats A. So both of these should be over 50%. And I want you to practice using these probability trees. So try it out. Pause now and go ahead. Okay. So that's a weird set of dice that I hope you found interesting. But this is just a game, right? It turns out that like this could happen in real life as well in a situation where things could make a difference. So you could have a situation where there might be different drugs that could work on different types of patients. And when I say different types of patients, I mean they might have a certain genes so that certain types of medicine might be more effective than the others. So it's kind of a situation between a dye versus, like a medicine versus a gene, which could be modeled with these different types of dice. And it might be possible that you have a situation that if you test drug versus a drug, maybe drug A tests better than drug B might test than drug C, and drug C tests better than drug A. That's a possible situation that could happen. So you might think about like how you evaluate these type of situations and what makes sense. Maybe you can think of other situation where the situation is not deterministic. Maybe there's some random element to it. And you could have a situation like this non-transitive dice type of situation. It's hard to wrap your head around because it's not intuitive, but it really does happen. Okay, so I promised you about a surprising game. So here's what it is. So Penneys Game. Penneys Game is invented by somebody, Walter Penney, whose last name is Penney. So that's why it's called Penneys Game. It's spelled differently from 1-cent coin penny, although you could use pennies to play this game. So what you do is first you pick a sequence of heads and tails, a sequence of length 3, and then you compete who gets their sequence first. So for example, if you picked HHT, heads, heads, tails, and I pick heads, tails, tails, we keep flipping coins until one of these appear first, and then you stop. So if you get tails, 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 heads, tails, heads, tails, so far these have not appeared. Heads, heads, tails. At this point, HHT has appeared, but HTT has not appeared on the sequence. So as soon as this appears, the round ends, and then you win, right? So let's play this game, and I want you to try it out yourself as well. So let's say I pick the sequence THT. So try to pick a sequence that you think will appear before this, and then play 10 rounds. And so you keep flipping until either THT or the sequence you pick appears, and then write down whether you won or lost, and then try to play this game 10 times. You could also use random.org coin flipper if you want a whole bunch of sequence of coin flips quickly. And then compute your winning percentage. You might first expect that, well, shouldn't this be 50-50? Because each of these sequence of 3 is equally likely to appear in 3 coin flips. And you might be right, but actually, if you compare until the first time something appears, the probability is not the same. You might find that surprising. So pick a sequence and then try it out. Pause the video and try it out, and then we'll move on. Okay, how did you do? Did you beat me? It turns out that there's a way to pick a sequence that's better than somebody else's sequence if you follow a certain procedure. So in this case, if I picked this sequence THT, it turns out that TTH is the best sequence that would beat my sequence. So I don't know if you got to pick that, or maybe you picked something else that was weaker than mine. It turns out that it's a non-transitive situation. So no matter what sequence you pick, there's another sequence that beats it. If you want to know how to pick this sequence, please watch this video. And then after you watch the video, try to describe your winning strategy on how to pick in your own words. Anyways, that's it. I think it's a fun game, Penny's Game. I like it. I'll see you in another video. All right, so in this for now.